Hello everyone, I am Payel Pandey from 6th Semester Geology Department, JK College, Purulia. Today I will discuss the topic fluid flow. As Pushpa has already discussed some portion of this topic, so now I will continue it from boundary effect. Let's first understand the boundary effect. To understand the boundary effect, for that we need to first know about free-flowing boundary layer and viscous sublayer. As you can see in the diagram, free-flowing is the portion of flow unaffected by the boundary effect. Next, boundary layer. It is the layer where velocity starts to decrease due to friction with bed and viscous sublayer. Viscous sublayer is the portion of reduced turbulence less than 1 mm thick decreases with increasing flow velocity. And the effect of the frictional drag existing between the sediment and the water flowing over it is to reduce the velocity of water near the bottom of the seabed or river bed. This effect is called boundary effect. Let's see what is velocity profile. Velocity profile shows the difference in intensity of resistance of fluid particles across the flow due to cohesive and adhesive forces. The laminar velocity profile of the fluid flow governed by the pressure gradient is parabolic, and the velocity profile for turbulent flow is fuller than for laminar flow. Let's talk about boundary shear stress. Boundary shear stress is determined by the force that the flow is able to exert on the sediment bed. It is an important variable in determining the erosion and transport of sediment on the bed below a flow. It is a function of depth, slope, and nature of fluid, and indirectly a function of flow velocity. Boundary shear stress is expressed as tau naught is equal to gamma rho GHS, where tau naught is equal to boundary shear stress, rho is fluid density, g is gravitational acceleration, h is flow depth, and s is the slope of the parallel bed. Now we will see the inertial forces and gravity forces are related. The ratio between the inertial force and gravity forces is Froude number. It is the dimensionless number and its mathematical formula is given as Fr is equal to U by root GL, where Fr is Froude number, U is mean velocity, G is gravitational acceleration, and L is water depth. Froude number helps us to decide the type of flow. If Froude number equal to 1, then the flow is termed as critical flow, and if the Froude number greater than 1, then the flow is termed as supercritical flow. If Froude number less than 1, then the flow is referred to as subcritical flow. Next, come to flow regime. A flow regime is essentially a description of the flow structure or distribution of one fluid phase relative to other. The hydraulic condition with Froude number less than 1 represent the lower flow regime, and the hydraulic condition with Froude number greater than 1 represent the upper flow regime. Now we will see what kind of bed forms are observed in different flow regime. In lower flow regime, ripples and dunes and transition bed forms are observed. In upper flow regime, plain bed, standing wave, and antidunes are observed. When flow velocity increases beyond the antidune stage, one final type of bed forms are observed: tube and pool. which are very uncommon in nature. There are three fundamental groups of transportational and depositional processes. They are passive suspension, entrainment flow, and sediment gravity flow. In passive suspension, due to lack of any vertical lift force or lateral force capable of moving particles, grains settle through a medium due to gravity. Entrainment flow. By this process, particles start moving, gradually becomes a part of the flowing fluid and subsequently being deposited from the fluid. Sediment gravity flow. In sediment gravity flow, sediments move down a slope due to direct action of the downslope component of gravity. Now, depending on rheology, sediment gravity flow may be classified as fluidal flow or Newtonian flow, and plastic or non-Newtonian flow. It is also called mass flow. Mass flow are of two types. They are mud flow or debris flow and grain flow. Similarly, fluidal flow may be subdivided into turbidity current, fluidized flow, and liquefied flow. Now we will see what are these flows. If the quantity of the mud is much higher than the coarser material, the flow is termed as mud flow. Grain flow. This is the downslope movement of cohesionless particles in high concentration due to sudden loss of internal shear strength of sediment. Turbidity current are a type of density flow where the bulk density exceeds that of the surrounding fluid by virtue of the presence of suspended sediment. Bomber sequence is formed due to turbidity current. Next, fluidal flow. The deposit of fluidized flow and liquefied flow are thick, poorly sorted sand unit with fluid escape structures such as descent pillar structure and pipe and sand volcanoes. These are the references. With this, we come to the end of our presentation. Thank you all.